Okay, this will finish the last video. So I mentioned a different type of test, chi-squared test. Chi looks like it's a lowercase x, so it's kind of like a fancy looking x. Chi is a Greek letter for ch, so it looks like an x. So chi-squared looks like kind of like a stylized x squared test, but it's actually called chi, chi. Chi-squared test. There's two variants. There's the chi-squared test of independence, and then there's the chi-squared goodness of fit. So we're going to go over those. These both deal with categorical data. So what if you're testing something to do with categorical data, like did it rain today? Yes or no? Did I roll a 2 when I rolled my dice? Or my die, I should say. Yes or no? Did I roll a 3? Did I roll a 4? Categorical data. Okay, so there's two variants of this. Present. One of them is when you're testing distributions. So, what days has it rained? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, whatever. Here we go. Frequency of rain. And frequency, again, just kind of means count or tally. So don't be put off by the word frequency. So let's say I went over the last, I don't know, so many days, and I wanted to figure out on which days, or let's say over the last, I don't know, it was a lot of days. On which days has there been rain? Well, let's say I have, I don't know, 6 Mondays it rained on, 3 Tuesdays, 1 of the Wednesdays, no Thursday, 4 Fridays, 2 Saturdays, and 1 Sunday. Let's say that's the distribution of days that it rained on in the last, I don't know, 10, 11, 12, 13, 14, 15, 16, 17 days. That's not very good. Let me make that, I don't know. Let me add a few. So I'll add 2 to this Thursday. So that gets me to 19. 20, 21. So that gives me to 21. I want that because that means there should be about 3 per day if they were split evenly. Now, if you can't split them evenly, you could put like a 2 here. Just get them as close to even as possible when you distribute them. But this becomes what you would expect if they're all equally likely. Whereas on the left, it could be all, I'm sorry, on the left is what you observe. So this is your observed, and on the right is what you expect. This is one way that you can do your goodness of, this is called a goodness of fit chi-squared. Sorry, tap the button. It doesn't have to be perfectly even. Let's say there are candies with red, greens, and blues, and let's say they claim that 50% of them are, let's say my data says I have 7 reds, 3 greens, and I don't know, 2 blues, 7, 8, 9, 5. So that's 13. Let's take it a little bit higher. We'll go to 15. So we'll do something like that. And let's say that someone claims that 50% of the reds, or 50% of the candies in this box, or from this company, 50% of the candies are red. So in that case, I wouldn't put evenly split. I would put what they claim the distribution is. So out of Am I at 14? I want to be at 15. So we'll make this a 5. So we're at 15. That means I would assume 10, 5, and 5, so that half of them are red. So this would be my expected. This would be my observed. So when I open the box of candy, I get 7 reds, 3 greens, and 5 blues. If 50% were red, I would expect 10 red, 5 green, and 5 blue. Whatever my total is, I kind of distribute it over the expected range according to what the claimed distribution is, or what the expected distribution is. If we expect 50% to be red, I would do it this way. If I expect every day to have an equally likely chance of it raining, I would spread it evenly, like I did over here. In either case, when you do a goodness of fit test, you put an expected distribution on the right side, or it doesn't matter what list you use, but you have an expected distribution. All you do is you add up all the tallies and distribute them how you think they should be distributed. Usually it's an even split, like over here. That's your expected column. And then you get data from the question or from your study where you get the actual distribution that you observed. So on 6 Mondays it rained, and 3 Tuesdays it rained, and 3 Wednesdays it rained, whatever. So you have those two columns. So to perform a goodness of fit test, to see if the distribution you observed matches the expected distribution, you would just do, you'd put it in your list. So edit the list. I would clear my list. 2 of my lists. And then I would put in, what did I say, 7, 3, and 5, and then 10, 5, 5. All right, so let's see if that fits. I have 3 possible outcomes when I draw candies, red, green, or blue. That tells me that what we call our degrees of freedom is 1 less than the length of this list. So if there's 3 outcomes possible, when they ask me what's my degrees of freedom, I'm going to say 2. I'm going to take 1 off of that length of list. So I'm going to go to chi-squared goodness of fit test. I'm just seeing if one distribution matches the other. My degrees of freedom is 2. 3 minus 1 is 2. And then I calculate. All right. I get a chi-squared test statistic. And I get a p-value, which is high. That's almost 43%. So if the distribution is true, if my expected distribution is true, that 50% are red, then seeing the data that I saw, where I had 7, 3, and 5 for how many reds, green, and blues I had, I'd have a 43% chance of that happening, given that that distribution is true for the whole population. So I can't reject that claim. That's too likely. So I would fail to reject, and I'd have to say, yeah, we'll go with the idea that the distribution is 50% red, and then 25% green, 25% blue. Because I don't have a small enough p-value to reject that claim. That's how you do a chi-squared goodness of fit test. There's another type of test for chi-squared. Mathematically, it works the same if we went over how these calculations are being performed, but it's called a test of independence. It could be males versus females, or Republicans versus Democrats, whatever you want. You've got 2 different groups here, categorical groups, not quantitative. And then they like this proposed bill. They don't like it. They don't care. Those are your options. So let's say that there are 15 men or whatever. 10 of them like it, 2 of them don't, and 3 of them are indifferent. Of the females, let's say that there's 10 of them, 7, or let's say 5 of them like it. I forget how many I said, 10. So 2 don't like it and 1 is indifferent. Or did I say 10? Yeah. So 3 are indifferent. So it doesn't have to be the same number. It could be different. to use your calculator, so what we're testing now, the default assumption is that this variable, their gender or their sex or their whatever this is, party affiliation, that this variable is independent of this variable, whether or not they like this legislation or not. So is variable 1 independent of variable 2? That's the default assumption. And the alternative assumption is that they're actually dependent, that whether or not you're male or female determines your likelihood of saying yes or no to this legislation. So the way you enter that is you'll go into your calculator. This time you actually have to enter in a matrix. So I'm going to go to second inverse to get the matrix. I'm going to edit matrix A. I had 2 rows and 3 columns, and I think I had, I'm just going to make up numbers, 10, 3 and 2, and 5, 2 and 3. So I put in my matrix for my observed there. And then if I need 2 matrices, I need the observed and I need the expected. So this is what I observed. The expected one I can go over in a different video, but the calculator does that for you. So if you're using the calculator, you don't have to enter it. Just go to your tests. This time we're looking for the chi-squared test, not goodness of fit. This is the test of independence, and it's just called chi-squared test. You go to that. My observed matrix is matrix A. Use matrix B to calculate the expected, and then calculate. And if you need to see the expected values, you can go to matrix B and check it out. But here's my p-value. So the probability that I would see what I did see, given the assumption that those 2 variables are independent, would be almost 60%. So it's very likely that if that were true, I would see what I saw. I would get my observation that I got. So that means I cannot reject the idea that they're independent. So I'd have to say those 2 variables are independent of each other. If I had a very small p-value, let's say 0.01, then I would reject the assumption that they're independent, and I would actually say that, well, your gender does affect whether or not you like the bill. They seem to be related. So that's the test of independence. So if you wanted to see if I went to matrix, I want to see matrix B. I'm going to press enter, show me matrix B. So those are my expected values. You can see it just by checking out matrix B. It was calculated automatically for you. You didn't have to put it in when you ran the test. You just would specify which matrix you want to choose. So that's the chi-squared goodness of fit. Does the distribution of outcomes for one variable, like color of candy, did it rain this day? That's one variable. I count what days it rained on, or I count what colors I got. And my degrees of freedom was 1 less than the length of the list. That was to see if my distribution that I observed matched my distribution that I expected for one variable. For test of independence, I have 2 variables, and I'm seeing if if one is independent of the other, or if they actually affect one another. In this case, they seem to be independent. If you have to calculate your degrees of freedom, so like if I ran that test again, it tells you. 2. How did they get that? Well, take 1 less than the number of rows, that's 1, times 1 less than the number of columns, that's 2. So 1 times 2 is 2. So my degrees of freedom here is 2. So that's how you'd use a calculator for any of those tests. So I hope that was clear. Have a good day.